Hello everyone, welcome back to my educational channel Gyan Wizard. I am Ajmal. In this video, we are going to derive the expression for acceleration and velocity of a body performing simple harmonic motion. The differential equation of a body performing simple harmonic motion is d square x upon dt square plus omega square x is equal to 0. We can write it d square x upon dt square is equal to the minus omega square x. D square x upon dt square, that is second derivative of the displacement, is nothing but acceleration. Acceleration A is equal to minus omega square x. This is the expression for acceleration of a body performing linear simple harmonic motion. When x is equal to 0, that means body is at the mean position. Acceleration A is also 0. When x is equal to A, that means body is at the extreme position, or specifically we can say when x is equal to plus minus A, then A will be equal to the minus plus omega square A. That means acceleration at the extreme point will be maximum, that is equal to minus omega square A in terms of the magnitude. Now let's derive the expression for velocity from the same equation. D square x upon dt square is equal to minus omega square x. Now here we have to find velocity in terms of the displacement x. We write it as d upon dt of dx upon dt is equal to minus omega square x. And dx upon dt, rate of change of displacement, is velocity. We can write it as dv upon dt is equal to minus omega square x. Here velocity is changing with time, but we have to derive the expression for velocity in terms of displacement x. We will change here to the dv upon dx dot dx upon dt is equal to minus omega square x. Dx upon dt is the rate of change of position with time, that means velocity. That means dv upon dx into v is equal to minus omega square x. Or we can write v dv is equal to the minus omega square x dx. Now integrating both sides means integration of v dv is equal to integration of minus omega square x dx, where omega is the angular frequency which is constant. We can take it out because constant from integration is always taken out of integration. We write it as minus omega square integration of x dx, and say the integration of v dv. We know that integration of x raised to n dx is equal to the x n plus 1 divided by n plus 1. Now use this formula here. Can write v square upon the 2 c is equal to the minus omega square x square upon the 2 plus c, where c is the constant of integration and we have to find out the value of c. When x is equal to a, That means the block or the oscillating body is at the extreme position. At extreme position, velocity is 0. V is equal to 0. Now put this value in this equation. V square means 0 square upon 2 is 0. This is equal to minus omega square A square upon 2 plus C. Therefore, C is equal to omega square A square upon 2. Let's put the value of the constant of integration C in this equation. We get V square upon 2 is equal to minus omega square x square divided upon 2 plus omega square A square upon 2. V square is equal to the omega square A square minus x square. Therefore, V is equal to plus minus omega root of A square minus x square. This is the expression for velocity of a body performing linear simple harmonic motion. Let's study the two cases. When x is equal to 0. When x is equal to 0, that is, body is at the mean position. Velocity V will be equal to plus minus omega root of A square minus 0 square, or V is equal to plus minus omega A. That means when the body is at the mean position, at equilibrium position, this velocity is maximum, whose magnitude is omega A. And when the body is at the extreme position, x is equal to plus minus A. Then this velocity V will be equal to 0. A square minus A square is 0, therefore V is equal to 0. That means when the body performing the linear simple harmonic motion is at the extreme position, its velocity is 0. So in a body performing linear simple harmonic motion, velocity is 0 at the extreme positions and is maximum at the mean position. Hope you find this video useful and informative. Please like it, share with your friends and subscribe to my channel. Thank you very much for watching this video.